Okay, we're gonna start in section 1.1, sets and functions. And as I said, I'll pretty much be following the book pretty closely. And start out with a little bit of definitions. If an element, say X, is a member of a set, say A, we say that X belongs to A. And write X with this funny backwards E symbol. X is in A. So that sort of just means X is in A. If X is not a member of the set A, we write X like this, and then put a line through it like this. If it's not a member, if X is not a member of A, we write it that way. And so that's just notation for membership of something in a set. Then if every element of the set A also belongs to B, belongs to B, we write A is a subset of B like this. Or sometimes you can even write it the other way, though it's a little bit unusual, but you can write it. We have the larger set on the left, and so you could write something like that. Oh, excuse me. If we write it this way, it has to go the other way like this. And again, usually they use this again. Basically, this just means subset. When you have this notation subset, like I say, it'll usually be written this way over here, where the smaller set will be here, the larger set will be here. So again, that just means subset. And we say, now technically, the way the definition is, A and B could be equal. All it says is every element of the set A belongs to B. So that doesn't exclude the case where they're equal. So this could sometimes mean that A could be equal to B. Now, if they're not equal, we call that a proper subset. We say A is a proper subset of a set B. If A is a subset of B, and there's at least one element or one member of B that is not an A. Oh, There you go. Thanks. We say that A is a proper subset of a set B if A is a subset of B and there is at least one element of B that is not in A. I think that's the way the book says it. In sometimes some books use a proper subset. Often a proper subset is written this way. Like this. Kind of what this other notation means, you can almost think of it like with less than or equal. You know how you have a less or equal sign. Well, this is sort of like what this means up here. A is either less than or equal to B. In other words, it could be, you know, a proper subset of B, or it could be equal to B. And then this is saying it's a proper subset, definitely sort of less than B. In other words, there are less things in A than there are in B. So again, it's the idea, you know, that you had before, where you had like the less than or equal and less than. And so that's just some notation for that part. And again, some of these are things, again, they're probably pretty logical and or you had them before, but we have to go through them just to be sure nothing's missed. And again, definition, I think this in the book, this gives it definition 1.1.1. Two sets are said to be equal and we write A equals B if A and B contain the exact same elements. Now later we'll be doing proofs. And so if we want to show that A and B are equal, we have to show the following. So to prove A equals B, we must show that A is a subset of B and that B is a subset of A. Because the only way those could both be true, if A is a subset of B and B is a subset of A, the only way that could be true is if they're equal. So later on, when we do proofs and stuff, that's how we'll have to approach it. We'll have to first show this is true, then show this is true, if we want to show that they're equal. And there's special sets that we're going to deal with, and you may or may not have had this notation before. Special sets, the natural numbers, and it's sort of a fancy N, sort of written sort of like this, and of course, they can write it better in the book, and that's defined as what they sometimes call the counting number. They always start at 1, 2, 3, 4, etc. Notice 0 is not included, the negatives are not included. Then there are the integers. And that's going to be, again, some fancy notation. Maybe something like this. The integers are going to be 0, minus 1, 1, minus 2, 2, minus 3, 3. Basically, all the whole numbers. Anything that doesn't have a fraction or a decimal or anything like that in it. And then we have the rational numbers. And they're usually designated by Q. And they're defined. I really should put double. What the double dots may just mean this is a definition of what these are, but it really means the same thing without the, but I'll write it this way. I think the book does it this way. Now, sometimes when you write sets, you can write it with something that's called set builder notation, where this consists of the m over n, all the m over n's, such that, and this double dot here, when it's inside the set, means such that. And some people use a vertical line instead. Write it this way, vertical. So some use double dots. Some, in any case, this is m divided by n such that m and n are integers. Like they're part of z, and not in the one in the bottom, and the denominator can't be 0. So they're all the rational numbers. Kind of the way that you can kind of remember them, that they're ratios. Rational numbers are ratios of numbers. That's where, I guess that's where the name rational comes from, ratios or fractions. They're like ratios or fractions of integers. Though, of course, when I say fraction here, you could end up having a whole number. You could have 3 divided by 1, so it could end up with whole numbers. But, of course, so these are rational numbers. And finally, we have the real numbers. And again, usually write with a fancy R. And that's basically all that's really all numbers except imaginary ones. And so it includes rational and irrational. Any questions on anything so far? Probably pretty straightforward. Okay, and just more background stuff. We'll do with set operations next. Once again, you've probably done this probably even in high school or even before that possibly. So the union of two sets say A and B are written this way, A and with sort of a big U in between them, B is say written as, and again, once you're using this sort of set builder notation, it's going to be X such that, once again, you use double dots here, or you can use a vertical line. I think the book uses double dots, so I'll do that. X such that X is in A. And so I think a lot of times they'll say or here, and that's what it means. But it also kind of means and or, because it can be in both. So it's all the values such that X is in A and or X is in B. So when you're putting the union two sets, it's everything that's in each one. And you don't repeat anything. And then intersection of A and B. A and the upside down U is going to be equal to all the X's such that X is in A and X is in B. Has to be in both sets, both A and B to be in this. And the complement with an E instead of an I here, I guess, of B relative to A is A. It's sort of written, it's sort of kind of like a slanted, maybe slanted like this B. And you got to sort of think of it as sort of a slanted minus, maybe that's a little bit longer. And it's going to be those X's such that X is in A and it's not in B. So remember, notation was not like that. And so, again, it's going to be anything that's in A, but you eliminate that anything, those ones that are also in B. And some other definitions: a set with no elements is called the empty set. And that's written as sort of an O with sort of a line through it. It's not phi, it's not the Greek letter phi. So it sort of looks like it. And then two sets are called disjoint if they have no elements in common. Of course, i.e. that would mean, say, so two sets A and B, if they don't have anything in common, if you take the intersection of the two, you would get nothing, so you'd get the empty set. And then visually, you could write these with Venn diagrams. Let me write that here. So, say, using Venn diagrams. So you maybe have something this, and say A and B are two sets from some bigger, in some bigger set. So let's say, let me make all the diagrams first, like this here. So then let's do the first one. Let's say, so if we do A union B, it would be, say, let me just write A union B will be the shaded area. So it'll be like anything in either set looks sort of something like all that shaded region there. And then A intersection B will be just the overlap of the two, something like this. And then A complement B. And remember the definition, it's anything that's in the set A, but not in B. So you can see that would be everything over here, because we don't want to include anything of A that was in B, so that's not included. So that'd be the way to represent those with Venn diagrams. And once again, you've probably done this a lot before, but let's just look at some examples over here. So let's say you have set 3, 4, 7, 10, 13. B is 4, 7, 11, 12, 15. And C is 3, 7, 10, 11. Find A union B. A complement B. A complement C, A intersection B, B union C, B intersection C, A must be union C, and HA minus B intersection C. So in fact, I'll go ahead and give you a minute if you want to try those. And if you're at home, you can pause the video. See, I lost my thing here. Yeah, pause the video if you want to do this and restart it. Okay. What did you get? Let's see. I'll write down some of the obvious ones first. Let's see, this one looks like this one was 3, 4, oops, I lose it here. Yeah, 3, 4, 3, 4, 7, 10, 11, 12, 13, 15. And yeah, then what did you get for B?
3, 10, 13.
Uh-huh. And what did you get for C?
4, 7, 13.
Let's see. Check the 7. Let's see. Was that? Pardon?
Okay, for C is. Oh yeah, it's not gonna be 7.
So just 4 and 13.
4 and 13.
Mm-hmm. That's all right. And then what'd you get for the next one?
4 and 7.
Uh-huh. And again, let me write these longer ones here. This is just a union, so not very challenging. And the intersection, we get 7 and 11 for F.
Yeah.
And then, okay, now let's see. Yeah, okay. Then what did you get for G?
I'm sorry, wouldn't E also have 4?
Let's see. For which one?
For probably
E. Yes, it should have 4 in it. Thank you.
Okay.
Yep, sorry about that. Yep, put a 4 right in here. Let me fix my paper over here. And then what did you get for G?
13.
Let's see, for 13, let's see, oh, you're right, just 13, huh?
Mm-hmm.
Oh, yeah.
Have a 4 also.
Oh, yeah, you know what, you're right. Because I messed up number E,
Right, so if you use.
I had a 14 when I wrote it down before, right? So that's just 13, huh?
Mm-hmm.
Okay, then finally what'd you get for H?
3, 4, 10, 13.
Uh-huh. Good. Okay. So that's pretty clear, huh? Okay. So now let's go to a theorem that they have in the book. And then we'll go ahead and try to prove it. I think will prove both parts. I think they just prove one of the parts in the book. We'll try to see if we can prove both parts. And this is 1 point. Let me get in. Let me move this over a little bit. Where am I at here? Okay, 1.1.14, like that. This is theorem. If A, B, and C are sets,
I think that's just 1.14.
oh, 1.14, 1.14 like that, huh?
Yeah.
Thank you. If A, B, and C are sets, then,
I'm sorry, 1.1.4.
oh,
There are 2 points.
okay, 1 point.
This is not 14.
Okay. Oh, I see. I'm sorry. 1.1 point for like that. Let's see.
Yes, like that.
Like that. Okay. Yeah. Too many ones in. Theorem. Okay. If A, B, and C are sets, then, and I'll just write the first part of the theorem now. Then we'll do the other part in a minute. A complement B union C is equal to A complement B intersection A complement C, like this. So again, I'll just do this one right now. So we'll try to prove that this is true. And so you remember to show two sets are equal, we must show that this is a subset of this, and then that this is a subset of this. So it must show the left-hand side is a subset of the right-hand side, and that the right-hand side is a subset of the left-hand side. So we'll do each of those. So first, we'll try to do this first part here. And so again, usually how you do this is first we'll let something be an element of the left-hand side. Let X be an element of A complement B union C, like this. And so we pick something on the left, and now we have to show, so that's going to be a typical element on the left. So we have to show that it is an element on the right. So that's what we eventually have to show. Let me just put that in parentheses. Must show that it's an element of the right-hand side, like that. So that's what we're going to be trying to prove. Just sort of keep that in mind. So let's say, so think about this. So we started with something on the left-hand side. It's an element of A complement B union C. So then what does this mean? If we then that means that, just using our definition, that means then then X is an element of A, but X is not an element of B, and X is not an element of C, huh? Because if you look at that definition, if something is in that set, it's got to be in A, and also, since there's a union here, that it can't be in B and it can't be in C. So now let's take that to the next step. So that means X is an element of A, but not an element of B. and X is the element of A and not an element of C. And so, of course, what does the and mean? The and means intersection, huh? So if X is in this set and X is in this set, that means it's in the intersection, huh? And that's what we were trying to prove. Because remember, we're trying to prove that this X, we started with the X over here, and we want to prove that it was in here. So therefore we showed that this is a subset of that, huh? Any questions on that? Okay, then we'll do the other way now. We're going to do the other side. So we proved that. So now we have to take something on this side here and prove that it's over here. So going the other direction then, let X be in A complement B intersection A complement C. And again, keep in mind, we want to show eventually show that X is in A complement B union C. So again, since X is in here, then that means X is in A complement B and X is in A complement C. So then that means X is in A, excuse me, X is in A, and that's also going to mean that X can't be in B, nor is X in C. So then this means then X is in A, and since X is in neither B nor C, that means and X is not in B union C because it's not in either one of those. So that means X is in A complement B, sorry, X is in A complement B union C, like this. So that means then A complement B intersection A complement C is a subset of A complement B union C, like that. Because that's what we wanted to show. Remember, we wanted to show that X was over here, which we did. So that proves that's a subset of that. So we proved that the first part, we proved that this was a subset of this. Now we proved this is a subset of this. So we have that A complement B union C, A complement intersection A complement C, like this, which is what we were trying to prove. They don't give the proof for the other, okay, there's another part of the theorem. Let me write that down. Let's see if we can work through that. See if we find any kind of complications there. So let's see. So the other part proof, once again, we're at 1.114. This was the other part. This was part B. It had A complement B intersection C, A complement B union A complement C, like this. So let's take a look at that. Like I say, the book didn't prove this part at all. So once again, we'll take something on the, let's see. Yeah, let me take something on the left-hand side this time. So let X be in A complement B intersection C. And then eventually what we're going to do, we want to show it's in the right-hand side. So we eventually show that X is in A complement B union A complement C, like this. Let's see if we can do this. So once again, just sort of following the definition, since X is in this, that means then X is in A and X is not in B intersection C. And so let's see. So X is in A and it's not in this. So that means, so X is, let's see, is in, let's see, maybe it did the, yeah, so X is in B and not in B intersection C. Yes, so that means X is X is not in B and or X, huh?
I think that's just and.
Pardon?
I think that one's just and. And this is intersection.
Yes, you know what? with the, and maybe this is where I made that I missed on the last one. So, for example, if it's not in the intersection, that means, you know what? Okay, I think it's maybe where I wrote it wrong before. That means, oh yeah, this is why this is probably maybe the line I should have put in the last one. So, see if it's not in B intersection C. Okay, that means it's not in B and or it's not in C.
Oh, that makes sense. because
Yeah.
It could be in B.
Yeah, it could be in B and not in C,
Yeah.
or it could be in C and not. And that may what maybe
Oh, okay.
maybe that's
probably what it was.
that's probably what I missed on the last one. Yeah, that's why I skipped. Okay, good. So that's good. I think we found out. So therefore, here we can say then. So if this is true, then X is not in a complement B, and or once again, X is not in a complement C. See if that sounds right. So it's in A and not in that intersection. Then that means X is in B and or not in C. So X is in a complement B and or X is in a complement C. So how if I do if something
Sounds
that
right.
doesn't make sense?
Yeah.
So then we can say again, because of the and or, so X is in a complement B union a complement C, like that. And that's what we were trying to prove. We were trying to prove that's true. So we can say, therefore, this side is a subset of the right-hand side. Like that. So now do the other part. And if we let X be in the right-hand side, like this, then that means, let's see, X is in a complement B. Let's see, and or X is in a complement C, like that. So, and we always have to keep track of what we're eventually have to go. We have to get to this part here. So then let's see, at this part we can say, so X is in A, let's see. Yeah, right. So because of this, because for it to be in this and or this, it has to be an A, huh? Because there's no, so that has to be true. And then also, let's see, since it's so, but it can't be in both B and C, huh? Because if it's in a complement B and or a complement C, it can't be taken away from both of these sets. Like for example, if it happened to be, yeah, if it happened to be an A, then if it's taken away by B, that's okay. But it cannot also be taken away by C.
Yeah.
So therefore, so if that's true, and X can't be in the intersection, cannot be in the intersection of B intersection C, huh? It could be in the union, but not the intersection, huh? Because if it was in the union, then it couldn't be in. Wait a minute. Yeah, right. Yeah, that's right. Yeah, I'll just say that. Don't want to complicate things. So now then, since this is true, so since X is in A and it's not in this intersection, then X is in A complement B intersection C, huh? And then so, therefore, A complement union A complement C is a subset of A complement B intersection C, like that. So therefore, we've proven what we wanted to prove. So finally, A complement B intersection C is equal to A complement B union A complement C, like that.